Okay, so in this video I'm going to be recording the solutions to the 2023 VCAA Exam 1. So this is a 1-hour paper, tech-free, no access to any notes or calculators of any kind. The standard maths methods formula sheet is provided, and I've got that here if we need to refer to it. So this was the first year of the first set of exams we saw of the new study design. There's not a significant amount of change from the previous study design to the new study design. Major things are no matrices anymore, so no matrix transformations, and the addition of pseudocode are probably the two main things. I think in the short term, certainly in 2023 it was the case, but I also think in the relative short term in this new study design we're unlikely to see pseudocode outside of multiple choice questions, is my gut instinct. Given the variability, I think you'd be unlikely to be asked to write any pseudocode. There are too many different ways to do that, and there are not enough conventions around the formatting of the pseudocode that would mean there'd be a lot of variability in the possible answers. And I think certainly while the assessing panel is relatively new to this content as well, I think that's unlikely to occur. So 2023, I'm recording this almost 12 months on from when this exam was sat. I completed the exam at the time, 12 months ago, and I recall on first looking at this particular exam 1 paper, so for example on reading time when you're reading through this looks like a very, very straightforward exam. It assesses really routine things, all things that we should know, but upon attempting the exam, I recall there's some quite challenging number work to be done, and so I think to that end it will have tested students' tech-free skills and their ability to handle a fair amount of algebra work and a fair amount of number work, which I actually think is not a bad thing for exam 1 to do. So content-wise, not difficult concepts, but really did thoroughly assess your number skills and algebra skills. Okay, let's get ourselves into it. So I'm coming to this cold. I haven't done this for 12 months, so let's see how we go. Okay, so page 1 of a tech-free exam, we're going to expect it to look like this pretty much every time. 2 derivative questions. 1, just straight find the derivative. The second, find the derivative at a point. They will be combinations of chain or product or quotient rules required. So first one, find and simplify dy dx. So y is obviously a quotient of 2 functions, so I'm going to use the quotient rule. If I'm at all unsure about the quotient rule, whether I've remembered it correctly, I'm going to make sure that I jump over to my formula sheet and I check what's happening on here with the quotient rule. The key place where you might go wrong with a quotient rule would be making sure that you get the subtraction around the right way. So it's going to be the derivative of the numerator multiplied by the denominator, and then we subtract and we leave the numerator as it is and we multiply by the derivative of the denominator and then over the denominator squared. So there's no excuse for getting these formulas around the wrong way. You've always got that formula sheet with you in both exam papers. Okay, so dy dx is equal to, so as I said, we're going to let's check. We're going to differentiate the numerator, so du dx, and multiply that by the denominator. So derivative of the numerator is just going to be 2x minus 1. And we're going to multiply that by the denominator, so this is going to require brackets. Use of brackets is always mentioned in examiners' reports. I should say poor use of brackets is always mentioned in examiners' reports. So if you didn't write brackets around that statement, it doesn't mean the same thing. Even if you wrote a multiplication sign, if you write 2x minus 1 times e to the x, that doesn't mean the same thing. The implied brackets there are here. Okay, and so you need to be really careful about making sure that where there should be brackets, there is brackets. Okay, so we've differentiated the numerator, multiplied by the denominator. We subtract for quotient rule. We'll leave the numerator as it is. And we'll differentiate the denominator. Derivative of e to the power of x. Again, if we're unsure, we can go back to our formula sheet. Derivative of e to the ax is ae to the ax. If we're differentiating e to the x, that's the example where a is just 1. And so the derivative of that's going to be 1 times e to the 1x. So it's just going to be e to the x. They absolutely should be rules that you know and don't need to check on the formula sheet, but please, if you're at all unsure, check it on the formula sheet. There's no excuse for getting those wrong. So it's going to be that over the denominator squared, so over e to the x squared. Okay, so there's a bit of simplification needed here because there's a common factor of e to the x in the whole function here. So there's actually and it does instruct in this instance, find and simplify. Okay, so what I'd be looking to do, you could do this in a couple of different ways. I'm going to take out that common factor of e to the x, and then in the bracket I'll have 2x minus 1 take away x squared minus x, and then we've got, that's going to be over e to the power of 2x. Okay, and so that e to the x is going to cancel with one of those e to the x's. And again, I'm going to expand and simplify the numerator. So I'm going to write that in descending powers of x. So I'm going to have negative x squared. I've got 2x minus x, so that's going to be plus 3x. And then I've got minus 1. And I've got that over e to the power of x. Obviously, you could also choose to write that as minus x squared plus 3x minus 1 times e to the negative x. But there's no reason to do that. It's fine as it is. If you, however, used a combination of product and chain rules to differentiate this, you probably would have ended up with the second one. Okay, B. Let f of x equal sine x times e to the 2x. So this is a product of two functions, a sine function multiplied by an exponential function. And so we're going to need to use the product rule. So again, we can go and check our product rule. Product rule is more forgiving because it is an addition in the product rule. And so, oh, sorry. I had the highlighter. It's an addition. Let's try that again. It is an addition in the product rule, and so the order that you do those two things in doesn't matter. Whereas the subtraction in the quotient rule means you need to be quite careful about that one. Okay, so we're going to have leave the first function as it is, differentiate the second function, plus, and we could do that in either order. I actually tend to do them in the other order because I always like to do it in the same order as I would use the quotient rule, so that I develop some habit there. Alright, so I'm going to differentiate the first function. So derivative of f, derivative of sine of x is cos of x. Again, I can check my formula sheet to check that rule. Multiplied by, leave the second function as it is, plus, we're going to leave the first function as it is, and we're going to multiply that by the derivative of the second function, which again we can check our formula sheet, will be 2e to the 2x. Okay, so then we can substitute. Now again, we could factor out e to the 2x and all those sorts of things, but there's absolutely no reason to do that. That's not our final answer, and even if it was, we don't need to do anything with this. One of the things I'm often trying to get through to my students is don't engage with the problem more than you need to. Every time you write down another line of algebra, the risk you run is that you make a stupid mistake in it. Okay, so if you've answered the question, you've differentiated, you're going to stop. In this instance, though, we're going to sub a number into it anyway. So even if this was horribly unsimplified, it wouldn't matter. I would just sub in the pi on 4, and then we could simplify it after that. So f dash at pi on 4 is going to be cos at pi on 4 times e to the 2 times pi on 4 is pi on 2, plus sine at pi on 4 times 2 times e to the 2 times pi on 4, which is pi on 2. Okay, so now we need our exact values for cos of pi on 4 and sine of pi on 4. I used my special triangles, so the pi on 4 exact values come from an isosceles triangle with side lengths of right-angled isosceles triangle with equal side lengths of 1. If you use Pythagoras' theorem, you can show that that's root 2. This angle there is going to be a 45-degree angle, because if this is 90 and it's isosceles, they're both going to be 45-degree angles, so pi on 4. And so we can use some good old Year 9 SOHCAHTOA trig to say, okay, well, cos of pi on 4 is adjacent over hypotenuse, and sine of pi on 4 is going to be opposite over hypotenuse. So 1 on root 2 for both of those. You do need to know your exact values, and you need to have a way to generate them in the exams. I prefer the special triangles because I like that it allows you to generate the answers from logic rather than rote learn some fact that you may or may not be able to recall accurately in the exam. But I must say, the pi on 4 exact values I don't generally need to draw the triangle for, because both cos and sine of pi on 4 are 1 on root 2, and tan of pi on 4 is 1, and I generally tend to remember those ones. But that's okay. So we're going to have 1 on root 2 times e to the pi on 2 plus 1 on root 2 times 2e to the pi on 2. Okay, so we could do lots of things with this. We'd probably answer the question at that point, but I'd probably just tidy up a little. So we're going to have tidy it up a little. So we're going to have e to the pi on 2 on root 2 plus 2e to the pi on 2 on root 2. In fact, I think it's probably not sufficient to stop here. There's quite a lot of simplification that can be done here. That's actually just collecting like terms, which would be expected. Okay, so we've got common denominator, so we've got e to the pi on 2 plus 2 lots of e to the pi on 2 over root 2. Now if you've got 1 lot of e to the pi on 2 and you're adding 2 lots of e to the pi on 2, you have 3 lots of e to the pi on 2 on root 2. There is no requirement to rationalise denominators in maths methods. Again, you could expend some energy rationalising that denominator, but there would be no reason to do so. If you did rationalise it, your answer would be 3 root 2 e to the pi on 2 on 2. So that's multiplying top and bottom of the fraction by root 2. But there is absolutely zero reason to do that. This is a perfectly correct answer here. Okay, question 2. Solve this exponential equation. This should be really routine year 11 work. So we need to recognise the sort of quadratic patterns that are happening in this. So we have e to the 2x minus, I'm getting everything on one side, minus 4e to the x minus 12. And some of you might be able to see that quadratic nice and easily there and go from there. I like to make a substitution so I can see the quadratic clearly. So I'm going to let u equal e to the power of x. Now remembering that e to the 2x actually is the same as e to the x squared. Okay, so what we have when we substitute for u is we have u squared minus 4 times u minus 12. And so it's a quadratic equation that can be solved. So we're going to factorise factors of negative 12 that add up to negative 4. That's going to be minus 6 and plus 2. And so we're going to get u minus 6 equals 0 or u plus 2 equals 0 using the null factor law. And so u equals 6 or u equals negative 2. But we're not solving for u, we're solving for x. So now we're going to substitute u equals e to the x back in. So we have e to the x equals 6. Or e to the x equals negative 2. Now this is not going to have any solutions. E to the power of something can't ever be negative. Think about the graph of e to the x. It's never going to equal negative 2. So this one doesn't have any solutions. You shouldn't need to get to the point where you write x equals log e of negative 2 to realise that doesn't have a solution. But this one will. We'll take log e of both sides and we get x equals log e of 6. So there's just the one solution to the equation. Okay, question 3. Sketch the graph of y equals 2 minus 3 on x minus 1 on the axis below, labelling all asymptotes with their equations and axial intercepts with their coordinates. Okay, so really routine, just a basic sketch of a graph. It is a hyperbola, so it might be easier for you to see and understand the transformations by rewriting it in this order. Okay, so this is going to reflect it in the x-axis, dilate it by a factor of 3 from the x-axis, translate it to the right by 1 and translate it up by 2. So you should be able to identify those things. So we're going to reflect in the x-axis, which means now if I was being asked to list the sequence of transformations, that is not a sufficient way to describe that, but I'm just informally making some notes so I know what's happening. If I reflect a hyperbola, the hyperbola normally goes in these two quadrants. If I reflect that in the x-axis, it's going to go in these two quadrants, so that's going to be the shape I'm dealing with. We're going to dilate by a factor of 3 from the x-axis. Again, this is very abbreviated. This is me just what's happening in my head, writing it on the paper. This is not an answer to a question that says state the sequence of transformations. We need to be much more formal in our language. And we are translating right 1 and up 2. So that's going to tell us where our asymptotes are. So that's the first thing I'm going to draw in. I'm going to have translated up by 1. So I'm going to have an asymptote here at y equals 1. If you are not very good at drawing straight lines, use a ruler. They say that every year in the examiner's report. So we've gone, oh, sorry, it was up by 2. It was right 1. Let's try that again. Good reason to always draw your graph with a pencil. You are allowed to complete your maths methods exam in a pencil, but you should make sure that it is a reasonably dark pencil, so HB or darker, so that it can still be seen when scanned. If you're concerned about it, go over your graph with a pen after you've drawn it, but do sketch them in pencil because graph shape is a really important component, and particularly with graphs with asymptotes, it's really easy to go off track with your shape, so be able to use a pencil so you can rub it out and fix it. Okay, right by 1 and up by 2, so that's going to be my asymptotes. We've talked about the shape, so my graph's going to be in these two quadrants here. So that means we're probably going to cross the y-axis somewhere here. We're going to cross the x-axis somewhere here. So let's work out those points so we can get those in the right place. So our y-intercept means we're going to let x equal 0. So we're going to have y equals negative 3 on 0 minus 1 plus 2. So that's going to be negative 3, so it's going to be 3 plus 2, and so my y-intercept is at 5. that makes sense with what I was thinking about as I plotted out where the graph would go. So we're going to cross there. And our x-intercept, we're going to have -3 on x minus 1 plus 2 equals 0. So I'm going to add that fraction onto the right-hand side. So rather than get negatives on both sides, let's keep things nice and positive. We're going to multiply by x minus 1. We're going to divide by 2. So we're going to have x minus 1 equals 3 divided by 2. And we're going to add 1. So 1 is 2 on 2. Adding that onto 3 on 2 gives us 5 on 2, which is 2.5. So it's really important that these points are accurately located relative to the grid. Okay, and then I want to draw in my shape. So I also want to just think about, I actually think them adding grids onto the graphs in the VCAA exams demands more accuracy from you, and I think you just need to be a bit careful to make sure that your graph is fitting the grid nicely. So I would probably just calculate a couple of other points. I'd probably just sub some values into this function. You know, for example, I might work out, you know, f at -1. Oh, sorry. And I'll probably try and do this in my head, but it's going to be 2 minus 3 on -1 minus 1 minus 2. So that's going to be 2 plus 3 on 2, which is 4 on 2. So that's essentially 2 plus 1.5, so it's going to be 3.5. So when x equals -1, it's going to go through 3.5, so we're going to go through there. When x equals -2, I'm going to think that through. So I'm just going to plot a few extra points in just to try and get, you know, the shape happening correctly. So, you know, f at -2 is going to be 2 minus 3 on -3. So it's going to be 2 minus 1, so 2 plus 1, so it's going to be at 3. Okay, and again, f at -3, or maybe I do another point over here, maybe we do f at 4. So 2 minus 3 on 4 minus 1, so that's 2 minus 3 on 3, so it's 2 minus 1. So it's definitely going to go through that point there. You know, you might calculate this f at 2 to get a sort of accurate point down here somewhere. So f at 2, if I put 2 in here, I get 2 minus 3 on 1, so it's 2 minus 3, so it's going to be -1. So you want to just plot out a couple of kind of key points. The other thing is that you can use the symmetry of the shape. So, you know, you can sort of think through where some of these points are going to be. So if we're, you know, if this is where my asymptotes meet, if I go left 1 and up 3, I should better go left 1 and down 3 to get to a point down here. So you can use some symmetry with the points that you've calculated as well. So I'm just going to get rid of those red scribbles. Alright, so let's draw our shape in, maybe even f at -3, so it'd be 3 on -4, so it'd be plus 3/4, so 2 3/4. So 2 3/4. So it's not going to be getting super close to the asymptote over this domain. So that actually also helps with your graph shape. You don't need to be getting very, very close to the asymptote. It's actually not appropriate to do so on this particular grid. Oh, just dropped a bit under that 5 there. Okay, then we're going to make sure that we've labelled everything we need to, because we haven't. Axial intercepts with their coordinates. So we're going to label this point here as 0, 5. And we're going to label this point here as 5 on 2, 0. We've got our asymptotes labelled with their equations, which we've done, y equals 2 and x equals 1. And we've so 3 marks is probably going to be your axis intercepts, your asymptotes, and shape. So shape for a hyperbola, we're looking for some symmetry. We're looking for good asymptotic behaviour. So that means if you've got an asymptote, graphs not running parallel to the asymptote, not veering away from the asymptote at the end, certainly not touching the asymptote. So you really do need to take some care. You also need to, with all graphs, make sure that you've drawn a smooth single line. So you can't draw your hyperbola like this, okay? Here, it's failing your vertical line test. It's not a function. You've got multiple functions happening there. And so you need to make sure that you have one nice smooth line. The other thing that's been mentioned in a lot of recent examiners' reports is about the concavity of a graph. Okay, so if the graph is meant to curve that way, it needs to curve that way, not that way. And I know that seems like an obvious thing, but I was actually marking something recently which was a truncus, and I found students when they were trying to make sure that their truncus hit certain points, they had a part of the graph that kind of went like that. Now that's where the concavity of the graph is incorrect. Your graph is curving that way when it should always be curving that way over that part of the domain. So you do need to make sure that you're really careful with your graph shape, and you take your time and you use a pencil and you correct it, and perhaps you go over your final line with a pen to make sure that things are clear. Okay, find the values of x for which f of x is less than or equal to 1. Okay, so we're going to use our graph to help us with this. So f of x is less than or equal to 1. So let me draw on the line y equals 1 here. So this is y equals 1. And obviously the black line is y equals f of x. So we are looking for where is the black line y equals f of x below the blue line y equals 1. Okay, so we're going to solve this inequality graphically, or be able to think it through graphically. So actually it needs to be less than or equal to. So we're going to include this point, which looks like it's happening at 4, but we'll confirm that algebraically. And it's going to include all of these points here. Okay, so those are all the x values where f of x is less than or equal to 1. So it's going to include -4, and it's going to include all of these values, but it's obviously not going to include the asymptote because the function can't be equal to negative. It can't be equal to, sorry, the x value can't be equal to 1. So let's just confirm that that point of intersection is indeed at 4. In fact, I think we already did that because we worked it out up here, didn't we? So we discovered that f of 4 was 3 because we did a nice accurate sketch. So that's actually helping us here. And so therefore, sorry, f of 4 wasn't 3, f of 4 was 1, 2 minus 1. And so we know that this point here is 4, 1, and so therefore we can see graphically that f of x is going to be less than 1, where x is somewhere between not negative 1, 1 at the asymptote, and up to 4, including 4. Okay, so when x equals 4, the y value will be 1. When x equals anything between 1 and 4, not including 1, the y value will be below 1. Okay, the graph of y equals x plus 1 on x is shown over part of its domain. Okay, so this is a sum of two functions, and we've been provided with the graph. Use two trapeziums of equal width to approximate the area between the curve, the x-axis, and the lines x equals 1 and x equals 3. Okay, so this is another addition to the study design in this new course, so it's not surprising to see this new content being assessed. So we are going to be approximating the area between the curve, the x-axis, the lines x equals 1 and x equals 3. Okay, so this is me drawing in the line x equals 3 here. I'm also going to draw in the line x equals 1. And then we want to approximate the area between the curve, those two lines that I've just drawn in, and the x-axis. Okay, so that is, we're going to be approximating this bounded area here using two trapeziums of equal width. Okay, so two trapeziums, let me go back to my pen. Two trapeziums of equal width. So equal width means they're each going to be 1 wide, so that's nice and easy. Okay. And we're obviously going to need to join up that point to get that first trapezium, and then we'll join up to there to get the second trapezium. So there is a formula on your formula sheet for the trapezium rule, but I think in many simple cases like these, it's more complicated than it needs to be. So if we just go over and look here, this bit I think is the bit that sometimes is unnecessarily complicated in terms of you actually understanding what's happening. Really, this is just half times the width of each trapezium. That's all that formula is doing. This is going to calculate the width, this divided by n, which is the number of trapeziums, that's going to calculate the width of each trapezium, and that 2 there is because of the half. Okay, so all that formula is doing, so area of a trapezium is always going to be half times h, which in this case is going to be that distance there, because it's the perpendicular height between the two parallel lengths, and then times a plus b. So this is just the half, this is just the h, which will be the width of each of our trapeziums, and then the a plus b is going to be obviously the value of the function at this first point. Okay, so if I reframe this thinking about it being on a graph, if this is my x-axis, this is A, this is B, and so therefore the y value here is f at A, and the y value here is f at B. Oops, sorry. And so therefore this would be times those two, the sum of those two heights. So in this case that would be f at A and f at B. So personally over here where I only need to work out two trapeziums, I would just work out the area of two trapeziums. I would stay away from this formula, but I'll go back to it and show you that it's going to give us the same response. So the trapezium estimate, sorry, go back to a black pen. Okay, so the first trapezium is going to be half times its width, which is just 1. So by that I mean this width, which in our traditional trapezium formula is the height. But that's because, you know, back in primary school when we learn about trapeziums, or early secondary school, that is, we usually draw a trapezium that way around. Okay, so our height is 1, and then times the sum of the two heights. So let's work out these two heights actually before we go very much further. So this is going to be 1f at 1. So if I put 1 into this function, I get 1 plus 1, which is 2. So that's the 0.12. We could probably read that off the graph almost. But be careful about that. You know, diagrams not drawn to scale, all that sort of thing. So make sure you're calculating information. When x equals 2, so putting 2 into here, we're going to get 2 plus a half. So that's 2.5 or 5 on 2. So this point here will be 2, 5 on 2. And as I said, it doesn't, if I'm, you know, perhaps haven't marked my point very accurately, but that, you know, just looks a bit under 5 on, looks a bit under 2.5. But, you know, calculating it algebraically is what you need to do rather than just guesstimate off the graph. And then when x equals 3, putting 3 in here, we're going to have 3 plus a third. 3 is 9/3 plus 1/3, so that'll be 10/3. So again, you might guesstimate that that looks like it's at 3, but it's not. It's actually just a bit above 3 at 3 1/3. Okay, so the two heights, so this is 2 and this is 2.5. So that is going to be 2 plus 5 on 2. And then my other trapezium is going to be half. Its width is also 1 because we needed two trapeziums of equal width. And the sum of its two heights is this. And so whilst this is a relatively routine question, all of a sudden we have quite a lot of fraction work to do here. And in my experience, students are not as good as are not as good at fractions as they should be at this point. All right, so we're going to have 1 half times 1 is just a half. 2 plus 5 on 2. Okay, so 2 is 4 on 2 plus 5 on 2, and so that's going to be 9 on 2. You need to be able to do that level of fraction work in your head. Okay, so then we're going to have half times 1, so it'll just be half, and in the bracket here, now I might need to do a little bit of separate work here, so maybe I'm going to write an extra step. So don't do steps in your head if you can't do them accurately. So I'm going to get a common denominator here which will be sixths. So the first fraction I need to multiply top and bottom by 3. The second fraction I need to multiply top and bottom by 2. Okay, so we're going to have half times 9 on 2, so multiplying the numerators, multiplying the denominators, so that's 9 on 4. Plus, we're going to have half times 15 on 6 plus 20 on 6 is 35 on 6. Okay, so we're going to have 9 on 4 plus 35 on 2 times 6, which is 12. And again, we're going to need a common denominator here. Now, be careful. You don't need to multiply two denominators together to get the common denominator. 4 is a factor of 12. So 12 is actually the common denominator. So we only need to adjust the first fraction. Sometimes I see students making much larger numbers than they need to. So multiplying top and bottom here by 3, 27 on 12 plus 35 on 12. And so 27 plus 35 is 55, 62 on 12. And so those are both even, so we also always need to give fractions in simplest form, and so that is going to be 31 on 6. So a little bit more than 5 is our approximated area. So, you know, again, you should be able to think about whether that makes sense at all. Obviously, this is 2, this maximum height is 3, so that rectangle there would have an area of 6. So I'm comfortable enough with 5-ish being a good estimation for this area. And just giving me that sense of, you know, does my answer make sense? You want to be asking yourself that regularly as you're working through the exam. Okay, so question 5. Evaluate the integral from 0 to pi on 3 of sine x dx. Okay, so this is really routine. Again, we've got our formula sheet with the rule for how to integrate sine x. So it's going to be negative 1 on a times cos of x. Obviously, a in this case is just 1, so it's going to be negative cos of x, the antiderivative. Okay, so the antiderivative negative cos of x from 0 to pi on 3. And so that is going to be, we're going to sub in pi on 3, negative cos of pi on 3 minus cos of 0. Okay, so again, we need to know some exact values. So for pi on 3, I'm going to use my special triangle, which is half of an equilateral triangle. And the reason an equilateral triangle is useful is because all of those angles are 60 degrees, so pi on 3, so there's a 60-degree angle there. If my equilateral triangle has a side length of 2, when I cut it in half to make a right-angled triangle, this length down here will be 1, and I can use Pythagoras' theorem to get root 3 there. So obviously, if this is a 60-degree angle here, pi on 3, this one up here is half of a 60-degree angle, pi on 6, and then we just need our traditional Year 9 SOHCAHTOA to be able to calculate all the exact values we need. So cos of pi on 3, cos is adjacent over hypotenuse, so cos of pi on 3 is going to be a half. So this is going to be negative a half. And then cos of 0 comes from our unit circle definitions of sine, cos, and tan. So cos is to do with the x-coordinate in the unit circle. So we want the x-coordinate when the angle is 0. That's what cos of 0 means. So the x-coordinate here is going to be 1 in the unit circle. And so minus is going to be plus, and cos of 0 is 1. So we've got negative a half plus 1, and so this is going to be 1/2. Okay, hence or otherwise. So hence means using this. Or otherwise means we don't have to use this, we can do it a different way. So hence or otherwise, find all values of k such that the integral from 0 to 3 of sine of x dx is equal to the integral from k to pi on 2 of cos of x dx, where k is between negative 3 pi and 2 pi. Okay, well we've just worked out what this, got the eraser there. We've just worked out that this thing here is equal to a half. Okay, so the question we're really solving here is integral from k to pi on 2 of cos of x has to equal 1/2. Okay, so integrals again, I can go back over my formula sheet. Integrating cos of x is going to give me 1 on a, but a is 1 in this case. Sine of x, so it's positive sine of x. So antiderivative here is going to be sine of x. And we're doing that from k to pi on 2. Alright, so we're going to substitute in pi on 2. So it's going to be sine of pi on 2 minus sine of k equals half. Now, exact values again, sine of pi on 2, again, is about the unit circle. So sine is to do with the y-coordinate in the unit circle. Pi on 2 is up here, that's an angle of pi on 2. So we want the y-coordinate here, and the y-coordinate up here is 1. So this is 1 minus sine of k equals a half. If we subtract 1, we're going to get negative sine of k equals negative a half. And so sine of k equals half. And so then what we end up with here is just a really routine trig equation to solve. So we're solving this trig equation over this particular domain. Okay, so I'm going to need, we've got the sine part of the equation on its own, which is the first step. We're going to need to think through a reference angle or using our exact values. So again, I've got the triangle up here. So we want sine to equal a half. So a half is, so let me get different color pens so you can see where I'm pointing. So a half, it means we're going to need these two side lengths. And for sine, sine is opposite over hypotenuse. So if sine has to equal a half, this one must be the opposite, and this must be the hypotenuse. And if that's the opposite, then we must be talking about this angle here. So our angle is pi on 6. So pi on 6, and we then need to understand how trig works in our unit circle. So sine has to equal positive a half. So again, sine's the y-coordinate. Here's where the y-coordinate's positive a half. So in the unit circle, that's going to mean we get a solution over in this quadrant and also solution over in this quadrant. Okay. So we're going to get this nice symmetry. Sorry, I haven't drawn a very symmetric circle there. So this angle here is pi on 6. We've just worked that out from our exact values. And this angle up here will be pi on 6. Now we want to think about our domain. So we want all of the solutions from negative 3 pi to 2 pi. Okay, so I'm going to think through the negative ones first. So if we think this is 0 here, this is minus pi here, this is minus 2 pi here, so I'm going in this direction, and this is minus 3 pi around here. So we want all of the solutions, and that's just the negative solutions in that domain. So it's going to be a solution up here and a solution around here. So this is minus pi minus another pi on 6. So pi is 6 pi on 6. So minus 6 pi on 6 minus another pi on 6. So that's going to be minus 7 pi on 6. And then this next solution around here, this is minus 2 pi, but we're going to add pi on 6 to get back to this one. So it's going to be pi on 6 before negative 2 pi, okay? And so negative 2 pi is the same as negative 12 pi on 6, but we're going to be pi on 6 before that, and so this is going to be negative 11 pi on 6. So that's my two negative solutions. So k is going to be negative 11 pi on 6 and negative 7 pi on 6. And now we can think through the two positive solutions, which are probably a little more intuitive. Just get rid of the bulk of that. Oh, got rid of the circle. Hold on. We'll need that. Okay, so alright, so then I need the positive solutions. So we also need to go from 0 around to 2 pi. So if this is 0 here and we're going around this way, we're doing one lap in this direction around to 2 pi. That's obviously pi that way around there. So if 0 plus pi on 6, that's nice and easy. And then the second solution around here will be pi minus pi on 6. And so that's going to be 5 pi on 6. And so our two positive solutions, pi on 6 and 5 pi on 6. So, you know, this is a really routine question, question 5. Integrate a very, very straightforward sine function. The rule for that's on the formula sheet. You need to know some exact values. And then solve another integral equal to a value which gives you a really, really simple trig equation to solve. So it's just knowing, this is really just knowing the basic skills. And honestly, being able to get full marks on question 5 here should be fundamental to you completing this course. Okay, question 6. Let p hat be the random variable that represents the sample proportion of households in a given suburb that have solar panels installed. From a sample of randomly selected households in a given suburb, an approximate 95% confidence interval for the proportion p of households having solar panels installed was determined to be 0.04 to 0.16. Find the value of p hat that was used to obtain this approximate 95% confidence interval. Okay, so the way a confidence interval works is it centers around p hat. So p hat has to be the middle of the confidence interval, and so therefore to find the middle of two numbers, the mathematical way to do that would be to average them, so to add them together and divide them by 2, that will give us the halfway point. So that's going to give us 0.04 plus 0.16 is 0.2 on 2, and so therefore p hat is going to be 0.1, which is exactly halfway between 0.04 and 0.16. Use z equals 2 to approximate the 95% confidence interval. Okay, so 95% confidence interval. Again, we can go to our formula sheet. We've got our confidence intervals formulas here. So, you know, again, refer to it if we need. So what they're saying here is for a 95% confidence interval, this Z score would usually be about 1.96, and you could actually get that really accurately on your CAS. But they're telling us in this question to just use 2 as an approximate, so we can do it by hand. So we're going to use 2 in that place, but otherwise we're going to have our rules. It's going to be p hat minus 2 lots of the square root of p hat times 1 minus p hat over n. And then it's going to be p hat plus 2 times the square root of p hat times 1 minus p hat over n. Okay, so in this case, that means we've got 0.1 minus 2 times the square root of 0.1 times 0.9 over, what's n in this case? So n is about sample size. Oh, we want to find n. Okay, sorry. My apologies, I misread the question. So we don't need to find the confidence interval, we were given the confidence interval. So rather than use the whole confidence interval, I'm just going to use one of the numbers. Okay, so I know that this 0.04, for example, or you could use the 0.16. So that is going to be p hat minus 2 times the square root of. Okay, so that 0.04, let me go back over here, is that expression is going to be equal to 0.04, or you could do this expression is equal to 0.16. Either way, maybe we'll do the positive one. So maybe we'll do that 2 plus, oh, sorry, not 2 plus, 0.1 plus 2 times the square root of, well actually, let's put the formula and then we'll put everything in. P hat times 1 minus p hat over n, that's going to have to equal the top end of the confidence interval, so 0.16. As I said, you could use 0.04 instead. So p hat is 0.1, Now, the other way that you could do it is if we've already worked out that p hat is 0.1, we already know that the margin of error is 0.06. So we're going to get to this point, but actually what we know by using this formula, but we actually know that that bit there is the margin of error, and that's going to equal 0.06. So we're going to get to that pretty quickly here, because when I take away 0.1 from both sides of this equation, I'm going to find that. Oh, sorry, I should put my 0.1 in here as well. So this is 0.1 times 0.9. So we know that this part, the margin of error part of the confidence interval formula, is going to be equal to 0.06. All right, so I'm going to divide both sides by 2, which means I get 0.03. And then I'm going to square both sides. An error that a lot of students make in solving equations with square roots is that they square root both sides, but this side's already being square rooted. You need to square both sides to undo a square root. So we need to be able to think about, we're going to have 0. Let's also do, sorry, that should be 0.9 up there. Let's also multiply those together. So 0.1 times 0.9. So again, there's some number work here to be dealt with. Now, if you're really uncomfortable with decimals, then I would write these things as fractions. So I would rewrite this as, 0.1 is 1/10, 0.9 is 9/10. So you could rewrite that numerator as that. 0.03 is 3 on 100. So you could work with fractions if you are much more comfortable in that area. I generally am more comfortable with fractions, but let's also, and that would probably be my default thing, but let's also think about the decimals, because these aren't overly complicated things to do. So we're going to have 0.1 times 0.9. So when you're multiplying decimals, you can just do 1 times 9, and then, so your answer is going to have a 9 in it, and then the number of points after the decimal place, if you count up how many points are after the decimal place in the original calculation, that is the total number of points you should have after the decimal place in the answer. So we're going to need 2 points after the decimal place. So 0.1 times 0.9 is 0.09. It's also important to bear in mind a does my answer make sense thing. If you're taking a fraction of a fraction, your answer should get smaller, not bigger. Okay. All right, so we're going to have, now that square and square root have cancelled each other out. We've got 0.09 on the numerator over n is going to be equal to, now 0.03 squared is 0.03 times 0.03. So we can do 3 times 3. There's going to be a 9 involved here, but we've got 4 numbers after the decimal place, 4 digits after the decimal place here, and so there will also be 4 digits after the decimal place here. So it's going to be 0.0009. Okay, I'm going to multiply by n and then divide by that. So I'm going to end up with n equals 0.09 over 0.0009. Now, if you are really not comfortable with decimals at this point, let's multiply the top and the bottom by 1,000 maybe. That might, sorry, by 100. No, let's do 1,000. That will get rid of the decimals completely. So multiplying by 1,000, decimal point is going to move 3 times. So on the numerator, we're going to have 90. Decimal point is going to move 3 times. Oh, sorry, I didn't do it enough, did I? Let's do another one. So let's make it 900 over, moving that decimal point 4 places, over 9, which means we're going to have 100. Now, you might have got there easier with fractions. You might have been much more comfortable with working with fractions, and that is fine. But you do need to be able to do this level of number work. And this exam in 2023, the concepts weren't difficult. The number work stumped a number of students who struggle with this sort of work. Okay, a larger sample of households is selected, so not n equals 100, a bigger sample, with a sample size 4 times the original sample. The sample proportion of households having solar panels installed is found to be the same. By what factor will the increased sample size affect the width of the confidence interval? Okay, so width of confidence interval is to do with the margin of error. Okay, width of the confidence interval is 2 lots of the margin of error. But let's just think about the effect on the margin of error, and then we can double that to work out what the effect is on the confidence, although it's a factor, so actually it'll be the same. So if the margin of error doubles, then the width of the confidence interval is going to double as well. Okay, so we really need to think about margin of error. And we need to think about what will happen if we increase the sample size, we make it 4 times bigger. Okay, so if we think about what's happening here, so it doesn't even matter, we actually don't even need to know p hat or anything here. Okay, so if we know that an original margin of error is whatever the z-score is, told us to let it be 2 in this problem, but actually it doesn't matter how big it is, times the square root of p hat times 1 minus p hat over n. And if we then change it, so let's say this is our original margin of error, and this is going to be our new margin of error, and we're going to get 2 times the square root of p hat times 1 minus p hat over 4n. So if we increase the size of the sample by 4. So if we look at manipulating this, this is just going to be, let's just leave that 2. This is going to be 1/4 times p hat times 1 minus p hat over n, which means this is 2 times square root of 1/4 times the square root of p hat times 1 minus p hat over n. So if we have a look at, if I just isolate that bit there, that's the only thing that's different when I went from this original margin of error to this new margin of error. Okay, so that's the only thing that's different. So in fact, all we've done is ended up with half, which is the square root of 1/4, times the original margin of error. So by what factor will the increased sample size affect the width of the confidence interval? So if we have 4 times as many people in our sample, the width is going to be halved. Okay, so therefore, increasing sample size by a factor of 4 will decrease the width of the confidence interval by a factor of 1/2. Now, I should be a bit careful about the wording there, because actually, if this had been a third, okay, if I wrote decrease by a factor of 1/3, that's actually not correct. We're ending up with 1/3 of the original margin of error. So it's a decrease by a factor of 2/3 if that's what happens. So just be a bit careful there, and perhaps I should have phrased that sentence a bit differently. So let me just reread the question and see if we could paraphrase it better. So, by what factor will the increased sample size affect the width of the confidence interval? So you could just say the width of the confidence interval will be multiplied by 1/2. That would be sufficient to answer the question, and then there's less sort of risk of misinterpreting the statement. But it's certainly not being increased by 1/2. We are multiplying the original margin of error by 1/2, so we're making it smaller, so there's a decrease happening there. So just be careful about how you answer that. It's a 1-mark question. You could also have done this numerically. You could have made n 400, worked out what the margin of error was, and worked out what effect that was 4 times bigger than this. But actually, this will be true regardless of all of the other numbers in the problem. For any margin of confidence interval problem, if you increase the sample size by a factor of 4, you're going to halve your the width of your confidence interval. Okay, question 7. Consider this function here. So it's a very basic parabola. Might be helpful for us to also think about it in a factorized form, because that tells us where x-intercepts are at 0 and 2. Obviously, the one at 2 doesn't exist because of the domain. So if we drew the full parabola, it would be this, but we have this domain only going from -infinity to 1. Having thought through the fact that the intercepts would be at 0 and 2, that means the turning point is definitely at 1. And so we are just looking at the left-hand side of a parabola, and this endpoint here is its turning point. It even looks like we can read off that the y value is -1, but obviously we would want to make sure algebraically that makes sense as well. If we put -1 in here, -1 all squared is +1, minus 2 times -1, so we're going to get plus, sorry, we're subbing +1 in. My apologies. So when x equals +1, we're going to get 1 minus 2, and so we get -1, so that definitely makes sense. Okay, so again, just taking a moment to understand the problem. I think sometimes we skim over this information stuff and launch straight into here, but have a look at it. What's the function? Does the graph match it? Obviously it does, but let me make sense of that and let me understand what's happening. Now let's think about our questions. So we're going to state the range of f. Okay, that can really clearly be read off the graph. We just algebraically confirmed that this endpoint here is definitely a 1, -1, and so therefore the range of f is going to be from -1, inclusive of -1, up to infinity because there is no endpoint here. This graph is continuing. The domain goes down to negative infinity. Okay, so a round bracket around infinity. Sketch the graph of the inverse function y equals inverse f of x on the axis above. Label any endpoints and axial intercepts with their coordinates. Okay, so you do not need to find the inverse function to sketch the inverse function. All that happens when we find an inverse function is we swap x and y. So this point here that was at 1, negative 1 is going to end up at negative 1, 1. Okay, so I'm just going to change the color there. So this point ends up being over here at this point at negative 1, 1. The other thing I would say is I would always, every time that I'm drawing in an inverse function, is I would also sketch in the line y equals x. Okay, I'm just going to do that with a pencil. So I need to make sure that my graphs are symmetric about this line. Okay, and so that's where this point ending up over here makes sense. That should be a right angle there, and indeed it is. Okay, so let's just plot out a few other points. The x-axis intercept is at 0, 0, and so when we swap 0, 0, we still get 0, 0, so it's also going to go through 0, 0, 0. Now the temptation here is sometimes when people go, okay, great, it's going to look like that. That is not a mirror image of that original shape in y equals x, and I know some students find it really hard to visualize the mirror image. So keep finding a few other points. This point, now, we could calculate it exactly. It doesn't really matter. It looks like it's roughly at negative 1, 3. So that means the inverse function will go through 3, negative 1. Okay. We could take a few other points. You know, this point here is at, I don't know, about negative 1/3, 1. It's not exactly that, but we just want to eyeball that. We just want to be able to see, okay, so if I go to 1, negative 1/3-ish. So again, I'm just making sure that that distance there is about the same as that distance there. Okay. So again, we could just plot out a few more points, whatever we need. This point here, you know, is at, I don't know, negative 3/4, 2. So we're going to be at 2, negative 3/4. Okay. And then we should have enough points to be able to join them up to sketch in a nice, accurate inverse function. So thinking about shape, obviously this is a turning point. So this should be a turning point here as well. It's going to go this way. Okay. What we have here is a sideways parabola. So we want to make sure that it's not just a straight line. We're going to be turning there. And by turning, I mean turning sideways. Okay. So let me go that again. So turning point here. So I'm giving some. Now see, as I just bent there, I've created a concavity problem there. So I'm using a pencil. I've rubbed it out. I'm going to go again. Okay. So. You know, you might even think about turning your page on its side. Oh, I've got it curving the wrong way again. You might even think about turning your page on the side so it's more like sketching a parabola than it is sketching a square root graph, and that might be easier for you to get the shape right. Okay, so in fact, I've just turned my laptop around sideways, and now I can't get the undo. Okay. Alright, so, and I'm going to try and draw it in a few pieces. Okay, so slightly missed that point there. I'm just going to erase that point there because that was just a sort of rough estimate one. Okay, but that's essentially the shape. So we should be seeing that mirror image. You should imagine if you were to fold, oh, sorry, I didn't mean the eraser. If you were to fold your paper across this line, try it. Think about it. Does that shape actually mirror it? Okay, so again, full mark. Everyone should be able to earn full marks at this question. Understanding what an inverse function and taking a bit of time. You did not need to find the equation of the inverse function to sketch the graph of it. Okay, but in part C, we're going to need to find the equation of it. Determine the equation and domain for the inverse function. Now, this is a really routine. This is a year 11 level question again. Okay, so inverse function, we're going to swap x and y. There is no y in the problem though, so you can't just say swap x and y when y doesn't exist in the problem. Okay, so I'm going to let y equal f of x, although I do think it actually said that in part A, that y is f of x, or somewhere I saw that up there. Doesn't matter. And then I'm going to be swapping x and y. So I can swap x and y, so x is going to be equal to f of y, which f of y is going to be y squared minus 2x. Sorry, y squared minus 2y. Now these days, I tend to not write this, I used to do that, but I tend to do these two things in one step, which means if I let y equal f of x and then swap x and y, I could straight away just say let x equal f of y. And that would get me straight away to here. But what is really important is that you are, clear about what you're doing and that you don't write something that's mathematically correct. Mathematically incorrect. So what you can't write is this line followed immediately by this line, because there's no algebraic step that takes you from that line to that line. They are not equivalent equations. We haven't done the same thing to both sides of that to get to there. We've done an unusual algebraic step, which is to swap x and y, and there must be that sentence between those two lines if that's how you're going to write it. If you're going to say y equals x squared minus 2x, then you need to explicitly say that you are going to swap x and y to get to that next line. As I said though, these days I tend to write straight away, we're going to do it all at once. So we're going to let f of y equal x, which means I'm going to get f of y, which is y squared minus 2y, equals x. Okay, so then we now need to make y the subject, and the problem with making y the subject here is there is multiple y's and they're not like terms and we can't collect them together. Okay, so we're going to need to understand a way to do this, and as I said, this is Year 11 Methods 101, okay? I would put this question on a Year 11 Methods exam every year if I could. It tests a number of different skills, because what we're going to need to do here is complete the square. Because we're going to need to understand that there are different ways of writing quadratics. They can look like this, but they can also look like this. And every single quadratic can be turned from this to this by completing the square. And the advantage of this version of a quadratic is there's only one instance of the unknown, whereas here we get two. So we're going to need to complete the square. So we test a lot of really good algebra skills by asking an inverse function that requires us to complete the square. So I'm going to complete the square on this left-hand side, which means halving -2 and squaring it. Half of -2 is -1, and squaring that is 1. So I'm going to add 1 onto that. And then I can't just add 1 because I feel like it, so I do the same thing to both sides. And so the left-hand side of my equation is now a perfect square. It is y minus 1 all squared. And that's going to equal x plus 1. And so what I've done by doing that is now create an equation where there is just one y, and I can now do the same thing to both sides until I get y on its own. So y minus 1, I'm going to square root, and when I take a square root, I get plus and minus. Again, a really important thing not to lose. The plus minus, and then we're going to add 1 to both sides. Okay, now we need to answer the question, which is to find the equation and the domain for the inverse function. So my answer to my question needs to be f(-1) of x equals something. Now it can't equal both of these. That is not a function. Okay, so this is where we go back to our graph, and our graph was really useful. So what we have, both of those square roots are this whole parabola. Okay, because it doesn't know that we didn't start with the whole parabola here. That came from this domain restriction. Okay, so if we'd had the whole parabola, which the equation without the domain restriction is the whole parabola, and we'd found the inverse, we would have had this whole sideways parabola. And that comprises two different parts. The top half of it is a positive square root, and the bottom half of it is the negative square root. It is two separate functions. Okay, positive square root top half, negative square root bottom half. So I can see from my graph that I have the inverse function here is the negative square root. And so my answer that I need when I state my inverse function here is the one with the negative square root. Okay, so we're going to have 1 minus the square root of x plus 1. Do not ignore the plus minus over here in this algebraic rearrangement. But when you then state your inverse function, it is only going to be one of those. Okay, so we've given the equation for the inverse function, so that's the first part. And we also need the domain for the inverse function. So when we sketched the graph, we swapped all the x and y values. So the same happens with domain and range. The domain, which is the set of x values, becomes the range, the set of y values, and vice versa. So the domain of the inverse function was the range of the original function, which is the answer we gave in part A, so -1 to infinity. Okay, again, really, really routine. Everyone doing Year 12 Maths Methods should be able to answer that question. Calculate the area of the regions enclosed by the curves of f f to the negative 1 and y equals negative x. Okay, so we've got f and f to the negative 1 drawn here. So the black line here is y equals f of x. The blue line here is inverse f of x. And then we want the areas enclosed with not y equals x, which I've drawn, but y equals negative x. So let's add that in as well. So y equals negative x is going to go through these points here. Actually, sorry, when I drew my inverse function, I didn't fully label it. So when I was asked to sketch the graph, label any endpoints and axial intercepts with their coordinates. Sorry, we didn't do this. So that was negative 1, 1, and the x-intercept 0, 0. Okay, so drawing in the line y equals negative x for my area question, it's going to go through here, it's going to hit there, it's going to go through the origin, and it's going to go through there, etc. Okay, so we have, and it gave us a hint in the wording, it said, calculate the area of the regions. So there are 2 regions, and we can see that. So we are calculating these here. Now everything is nice and symmetric here, so we can just calculate one of these areas and double it. So we can either do the integral from 0 to 1 or the integral from negative 1 to 0. Probably going to do the integral from 0 to 1. I like to keep things positive. Okay, so the area that we need here is going to be 2 times the integral from 0 to 1. And we're going to integrate. When it's area between 2 curves, it's the top curve minus the bottom curve. So the top curve in this instance is this line, y equals negative x, minus the bottom curve. The other advantage of finding this region rather than this region is that I'm going to be able to use the original function. And if you have a choice in any question between using a function you calculated versus a function you were given, you're always going to choose to use the option that is the function that you were given. So it makes complete sense for us to be finding this area here because we're using the original function, not the inverse function that we calculated. It's also going to be much easier to integrate x squared minus 2x than it is going to be to integrate the square root of x plus 1. It's not awful, but it's just a bit nicer. Okay, so we're going to be integral of top function, which was negative x, minus the bottom function, which was the equation that we started with, which was, sorry, I've forgotten already, x squared minus 2x. Okay, now before we launch into any anti-differentiating, there's some like terms here. Let's simplify things before we do anything. So the area is going to be 2 times the integral from 0 to 1. We're going to have negative x minus 2x. That's negative x plus 2x. So that's going to be positive x. Okay, now we're ready to anti-differentiate. So we're going to have 2 times antiderivative of x is x squared on 2. Antiderivative of x squared is x cubed on 3. And we're doing that from 0 to 1. We're going to have 2 times. Now make sure it's 2 times your whole answer. So this is where it gets, you need to be a bit careful here. So we're going to substitute 1. So we're going to get 1/2 minus 1/3. And then we're subbing in 0. So actually it's just going to be 0 minus 0. Be careful about just assuming whenever you sub in 0, you get 0. Obviously, if this was a cos function, cos of 0 isn't 0. If this was an exponential function, e to the 0 isn't 0. So I always make sure that I write out the substitution step, just so I can be clear I haven't missed anything. Okay, so we're going to have 2 times 1/2 minus 1/3. So we're going to need a common denominator there. So that's going to be sixths. So top and bottom of the first fraction multiplied by 3. So we get 3/6 minus top and bottom multiplied by 2, 2/6. So we're going to have 2 times 1/6, which means we have 2/6 or 1/3. You do need to simplify your answer. That's an area, so it's going to be in square units. Okay, question 8. Suppose that the queuing time, t, in minutes at a customer service desk has a probability density function given by this. Show that k equals 1 on 64. Okay, so obviously it's a probability density function, and so therefore the total area has to be 1. So we therefore need to show. So we don't use this answer to show that it's the answer, okay? We need to use other information to arrive at an answer of k equals 64. Sorry, just paused for a minute there while I got my eraser working again. Okay, so we know the total area. So in this instance, that's going to be the integral from 0 to 4 because that's the total domain of the probability density function. Well, it has domain elsewhere, but it's non-existent. There's no area under that anywhere else. Integral from 0 to 4 of our function, k times t times 16 minus t squared. has to equal 1. Okay, now I'm not usually a big fan of taking constants out of integrals, but in this case I would. The k can come out of there and then I can divide it over onto this side. So I'm going to do that and just get it out of the way over onto the right hand side while I focus on the integral, and then we'll see where we end up. So we're going to have integral from 0 to 4 of, now I'm also going to expand out these brackets so that I can integrate, so I'm going to have 16t minus t cubed, and the k I took out and divided over here, so this is going to equal 1 on k. Okay, so now we can integrate. Antiderivative of 16t is 16t squared on 2, so that's 8t squared. And antiderivative of t cubed is t to the 4 on 4. Doing that from 0 to 4, and that equals 1 on k. It's a show that, so you don't want to be skipping steps here. You need to be clear, have a clear logical process that arrives at the answer of 1 on 6, k is 1 on 64. Okay, so I'm going to substitute 4 into this. So we're going to have 8 times 4 squared minus 4 cubed on 4. Now, I remember the number work here, and obviously it'll be minus 0 when we put 0 into that. The number work here caused quite a lot of problems and throughout this question, but it was because students weren't working smart with the numbers, okay? So for example, 4 cubed on 4, I don't need to work out what 4 cubed is. It is 64 and that's not awful, but I don't need to work it out because I actually have 4 cubed on 4 to the power of 1, and if I use my index laws here, 4 cubed on 4 to the power of 1 is 4 squared. And so it's about being efficient with what you're doing here, okay? So we're going to have 8 times 4 squared minus 4 squared. So again, the other thing you might do is you might not even expand that out. You might leave this as 8 times 4 squared minus, we've just worked out that's going to be 4 squared. And then obviously it's minus 0 equals 1 on k. So 8 lots of 4 squared minus 1 lot of 4 squared is just 7 lots of 4 squared. So again, it's about being able to be flexible with your number work. My apologies, I just realised that we've made an error back here. I've made an error back here in that somehow this power of 4 became a power of 3. So let's go back and fix that. So that's actually going to be a power of 4. Okay, so my apologies. So 4 to the 4 on 4 is going to be 4 cubed. So again, I don't need to work out what 4 to the power of 4 is. Use my index laws. So we're going to have 8. Oh, sorry. It's going to be 4 cubed. So we are going to now need to be able to work this out. So we're going to have 8 times 16 minus 4 cubed is 64. 4 times 4 is 16 and times 4 again is 64. Minus 1 on k. 8 lots of 16. 8 tens is 80 and 8 sixes is 42. Sorry, 48. So we're going to have 80 plus 48, so we're going to have 128 there, minus 64. And so 128 minus 64 is 64. And so therefore 1 on 64 is going to be equal to k if we take the reciprocal of both sides. Okay, so then we want to find the expected value of t. So expected value of t, so this is about knowing about our continuous probability distributions. So it's going to be the integral over the total domain of t times our function, f at t. Okay, so we're going to need to do integral from 0 to 4 of t times, now k is 1 on 64, so our function is 1 on 64 t times 16 minus t squared dt. Don't forget your dt's. Okay, so we're going to need to expand things out a little bit here before we can integrate. Alright. We're going to have, so essentially what we have is t squared out here. We've got 1 on 64 times t squared, okay? So we're going to have 16 on 64 times t squared when we expand that out, and then we're going to have minus 1 on 64 times t cubed. Now, if you want, you could actually take your 1 on 64 out of here, and in fact, as I said, I don't often recommend taking a constant out because sometimes it's useful, but actually taking a fraction out is going to not be a bad thing to do in this instance. So what I actually might do is write this as 1 on 64 integral from 0 to 4 of 16t squared minus t cubed. Now, I didn't have to because we could have simplified that. That's just going to be a quarter, and so it might be nice to just leave that as that. So either way, there's pros and cons. And as I said, generally speaking, I'm not a fan of taking out constants, but I'm not loving having all those 1 on 64s everywhere. Although, as I said, this is just a quarter. So just making sure that you simplify things before you go ahead with them. But let's go with it this way. So let's leave the 1 on 64 out here. We anti-differentiate, so antiderivative of 16t cubed is going to be 16t squared is going to be 16t cubed on 3 minus t to the 4 on 4, and we're doing that from 0 to 4. So we're going to have 1 on 64. See, and now maybe I'm regretting taking out the 1 on 64. I've sort of just got fractions everywhere. So, we didn't avoid having fractions in here. So rather than having a separate fraction out here, I've now got 3 fractions to deal with where I could have only had 2. So in fact, I'm going to go back and stick with what I usually preach, which is stop taking the constants out. They generally doesn't help you. It just leaves you with an extra constant that you might miss multiplying back in later on. Okay, so we're going to have... Okay, so I'm going to leave that in there, which means we're going to have integral from 0 to 4 of 1/4 t squared, which is just t squared on 4, if you prefer to write it that way, minus t cubed on 64. All right, anti-differentiate. So we're going to add 1 to that power, which means it becomes 3. We divide by that power, so we're going to get a denominator of 12. So t cubed on 12 minus add 1 to that power becomes 4. We're going to divide by that power, and that's going to become 64 times 4. Now, what's going to happen here is I'm going to have a lot of powers of 4 when I substitute the 4 in. So rather than me work out what 64 times 4 is, what I might instead do is 64 is 4 cubed, and then timing that by another 4 again, this is going to be 4 to the power of 4 on the denominator here. And it's going to save us a lot of work here, because when I then sub 4 to the power of 4 into here, I'm going to be able to see that more clearly. It might even have been helpful for you to have just left it written as 60. Sorry, I'm having trouble with the eraser at the moment. Just left it sitting as 64 times 4 if you'd prefer. Okay, so you could do it this way. We could just say, okay, that's just going to be 64 times 4. Either way. Okay, so what we essentially have here is t cubed. In fact, I might leave that as 3 times 4 as well, because that might be useful. Minus t to the power of 4 on, that's going to be 4 to the power of 4 from 0 to 4. All right, I'm running out of page here. Let's see how we go. So putting 4 into that, we're going to have 4 cubed on 3 times 4 minus 4 to the power of 4 on 4 to the power of 4. And then obviously take away 0. So leaving them as powers is going to be useful here, because I'm going to be able to cancel this 4 with one of those 4s. And then obviously I get 1 with the second fraction here. So we're actually going to end up with 4 squared on 3 there, minus 1. So that's going to be 16 on 3 minus 1. And we haven't in any way had to work out what 4 to the power of 4 is. So I found a lot of students ended up with very big numbers here. So 16 on 3 minus 1, which is 3 on 3. And so we're just going to get 13 on 3. So it's about being strategic with your number work. My apologies. I just realised I made pretty much the same error I made before. Sorry, it's quite late. I've had a long day. I'm tired. Sorry, that was a 4 there. But I didn't actually integrate. No, I mucked up right back here. Okay, let's go back here. So we have t squared outside here, and we needed to times that by t squared. And so actually that should be a power of 4. Okay, so let's fix things. Oh, sorry. I said I'm having trouble with the eraser at the moment. Okay. Now again, sometimes you're better to just go back to the beginning. Sometimes fixing things, you're going to miss errors. So I'm just going to be quite careful about everything here. And let's get rid of everything from here onwards. Sorry, my computer's got a bit hot and bothered. It's going a bit slow at the moment. Okay, so as I said, this should have been a power of 4 back there. Okay, so that means this is a power of 4 here. And then that means when we integrate, we're going to have t to the power of 5 on, that 64 will still be there, but let's just leave that as 64. In fact, let's write the 64 as 4 cubed times 5. Okay, so here we have t to the power of 5 on 5 times 4 cubed, or it doesn't matter, you can write that the other way around. Okay, so now when we put 4 in here, we've got 4 to the power of 5 on 5 times 4 cubed. So again, I don't need to work out what 4 to the power of 5 is. I don't need to work out what 4 cubed is. I'm going to use my index laws here to simplify things. All right, so let's go back to my black pen. So 4 cubed on 4 in the first fraction, that's going to mean we get 4 squared, and the 3 will still be on the denominator there. 4 to the power of 5 on 4 cubed means we're going to get 4 squared, and there'll be 5 in the denominator there. Okay, so now we have 16 on 3 minus 16 on 5. So we need a common denominator, which is going to be 15. So we need to get to some biggish numbers, but not enormous numbers. So we're going to multiply 16 by 5. We can do that lots of different ways. Again, flexible number work's important. We could do 16 times 10 and halve it. That's the same as multiplying by 5. So it's going to be 80. Or we do 5 tens is 50 and 5 sixes is 30. So we're going to get to 80 on 15. Minus, second fraction, we need to multiply top and bottom by 3. 3 16s, 3 10s is 30, 3 sixes is 18, so we get 48 on 15. So 80 minus 48 is going to be 32 on 15. So once again, strategic number work saved us a lot of time here, and obviously time is of the essence. Also, it was less prone to error than if you had, saw students with a lot of enormous calculations, working out what 4 to the power of 5 was and what 4 cubed was, and then trying to simplify those things, okay, rather than recognizing that 4 to the 5 on 4 cubed is 4 squared. Part C. What is the probability that a person has to queue for more than 2 minutes given that they have already queued for 1 minute? Okay, so we want probability that t is more than 2 given that t is more than 1. So conditional probability means we need the intersection of those two things. So if t has to be both bigger than 1 and bigger than 2, it just is bigger than 2 over the second thing. Okay, maybe let's take a minute to work out those two things separately, just because we're going to get things that would get a bit messy otherwise. So probability that t is bigger than 2 means we're going to integrate from 2 to 4. And so we're going to integrate, let's just get our function again. What is it? 1 on 64 times t to the power, t times, just trying to make sure it's right. Times t times 16 minus t squared. Okay, so that is the integral from 2 to 4 of, let's expand that out. So we're going to have 16 on 64, so it's just a quarter. So it's going to be t on 4 minus t cubed on 64. Okay, so antiderivative, add 1 to our power becomes t squared, divide by that power, so it'll be on 8. Minus, add 1 to the power, t to the power of 4, divide by that power. Now we've already got 4 cubed on the denominator here, so if we're multiplying that by 4 again, we're going to have 4 to the power of 4 on the denominator. Sorry, not 0. 2 to 4. Okay, so subbing in 4, we're going to get 4 squared on 8, so that's going to be 16 on 8, minus 4 to the power of 4 on 4 to the power of 4. And then we're going to take away, we're going to sub in 2. 2 squared is 4, so we have 4 on 8, which is a half, minus, now here we're going to have 2 to the power of 4 on 4 to the power of 4. Okay, so we can do a couple of different things here. So 16 on 8 is 2, obviously. Could have done that straight away. 4 to the 4 on 4 to the 4 is 1. Minus, now this bit here we could think about in a couple of different ways. 2 to the 4 is 16, which is 4 squared. So we've got 4 squared on 4 to the power of 4. 4 to the 4, which means we have 1 on 4 squared, which means we have 1 on 16. The other way we could do it is when both the numerator and denominator have the same power, that's the same as 2 on 4 all to the power of 4, which is the same as half to the power of 4 which is the same as 1 on 16. Okay, so lots of different ways we could think that through, okay, to get to 1 on 16 without needing to work out 4 to the power of 4. So we're going to have 2 minus 1, sorry, let's just do that. 2 minus 1 being 1. And then we're going to have minus a half, and minus minus will be plus, and that's going to be 1/16. Alright, so 2 minus a half, sorry, 1 minus a half is a half, plus 1/16. 1 half is 8/16 plus 1/16, and so that's going to be 7/16. Okay, so I've taken up a lot of space with that. Let me get these scrolls out of the way. Alright, then we also need the probability that t is bigger than 1. So that's going to be the integral from 1 to 4. Now the other way you might choose to do this would be to do 1 minus the integral from 0 to 1, and that just gives you a bit less substitution to have to do if you get to sub in 0, so that could also be an efficient way to do it. Now I'm going to jump ahead a bit to this simplified version that we did the work on over here, so we're going to straight away write in that this is t on 4 minus t cubed on 64. We've already worked out the antiderivative. It's t squared on 8 minus t to the 4 on 4 squared, sorry, not 4 squared, 4 to the 4. And we're going from 1 to 4. So we're going to substitute in 4. Now we already did that here, over here. When we subbed in 4, we found that it gave us 1. Okay, so let's just go straight to that. So we know it's going to be 1 when we put 4 into that, minus, and then here we're going to have 1/8 minus 1 on 4 to the 4. Now 4 to the 4 we probably need to think through here. Although perhaps rather than doing that, now I'm not sure how efficient this is going to be, but if we, given that we're going to need a common denominator, this is 1 on 2 times 4, and this is going to be 1 on 4 to the power of 4. So if I think about the common denominator, I only need to multiply the top and the bottom here by the top and the bottom on the left by 4 cubed, and the top and the bottom on the right by 2. Now that's not the lowest common denominator, but it's at least going to get me to a place where I can put them together. So it's going to be 4 cubed on 2 times 4 to the 4 minus 2 on 2 times 4 to the 4. So we've got a common denominator of 2 times 4 to the 4. And so we're going to have 4 cubed, which is 64, minus 2 all over 2 times 4 to the power of 4, which means we're going to have 1 minus, what did I say, so 62 on 2 times 4 to the 4, which means it is 1 minus 31 on 4 to the 4, so I've just got rid of that 2. Okay. Sorry, in all of that we should have thought through our common denominator with this 1 as well. So this is 4 to the 4 on 4 to the 4. I think we might finally need to have to work out what 4 to the 4 is. 4 cubed is 64, and so we need to times that by 4 again. So 4 4s are 16, 4 6s are 24 plus 1 is 25, so 256. So we're going to get 256 minus 31, so that's going to be 225 on 256. Okay, so now 256 is 4 to the 4, remember. So again, it still might be helpful for us to have this one as 225 on 4 to the power of 4, and this answer here is 7 on 4 to the power of 2. Just in terms of what we're going to need to do is divide them. My apologies, I've just realised I've made an error over here. As I said, shouldn't be recording this so late. 8 plus 1, so we should have 9 here. Sorry, I just had a look at the answer before and I thought, I don't think there's any 7s involved. I just went back and had a check. So we should have got 9 there. Okay, so now let's put things back together. We've worked out the numerator and denominator of our conditional probabilities. The numerator is the 9 on 4 squared. Okay, so this means we're going to have 9 on 4 squared divided by 225 on 4 to the 4. 225 on 4 to the 4. This is why I've left them as powers. So we're going to have 9 on 4 squared times 4 to the 4 on 225, which means that is going to cancel with 2 of those. So we're just going to have 9 on 1 times 16 on 225. Now again, fraction work is always about trying to look if you can cancel before you multiply them together. So I don't want to do 9 times 16. And actually, if I recognize 225, 250 is going to be 25 times 10. And so actually, 225 is one lot of 25 less than that. It's 25 times 9. So there's a common factor of 9. Oh, sorry, I'm still having trouble with this eraser. Try again. Okay, so there's a common factor of 9 between that 9 and that 225. So this is going to be 1. I'll go back to the black pen in a minute. And that's 25. And so what we end up with here is our final answer of 16 on 25. Okay, so we just took an offshoot to work out that integral, we took an offshoot to work out that integral, and then we've come back up here to the top and found that our conditional probability is 16 on 25. Now this question really stumped students. There's a lot of number work, a lot of fiddly things going on, negatives and powers and lots of powers of 4 and potentially big numbers. So again, it's about being strategic and about being really careful. And look, I made an error down here and may well have ended up, you know, with a 7 involved up here instead of a 9 and therefore got the wrong answer. But all you can do is just go step by step and take things simply, but try to look where you can simplify as much as you can go. Can you simplify the fractions? Can you leave things as powers of something which would make it easier to simplify them later on, etc. Okay, question 9. All right, so this is the last question of the exam. The shapes of 2 walking tracks are shown below. So we imagine we're looking at a map, a bird's eye view of a map. And we've got a dotted line track, which looks like a parabola, and we've got a solid line track, which looks like it might be some sort of cubic or some other polynomial. Okay, so we've been given the functions. Track 1 is described by the function f of x. Okay, so track 1 is the cubic looking line, and indeed that is a cubic function. If you expand that out there, you're going to have an x cubed involved there. And track 2 is defined by the function g of x, which is a parabola. The unit length is in kilometres. Given that f of 0 is 12, g of 1 is 9, verify that a equals 12 and b equals negative 3. So you can't substitute this into this and this into this. Okay? So you need to use this information given here in order to verify that that thing is true, not the reverse. So f of 0 means we get a minus 0 times 0 minus 2 squared. And again, it's like a show that, so don't skip the steps. Be clear about what's happening. So this means we're going to have a minus 0. So this 0 out the front just means that whole thing there is going to be 0. And what did f of 0 equal? It equals 12. So a minus 0 equals 12. And so a equals 12. Okay, so it's a fairly straightforward show that or verify. So make sure that you are clear about the steps. All right, and then the other one is that, g of, all right, we'll get there again. G of 1 is equal to 9. So substituting 1 into g of x means we get 12 times 1 plus b times 1 squared. So again, be clear about what's happening. Subbing 1 into g is going to be equal to 9. And so this gives us 12 plus b equals 9. And so therefore b is 9 minus 12, which is negative 3 as required. Okay, so relatively straightforward, but just don't skip over the steps. Okay, you need to show it, verify it, give evidence for it. Part B, verify that f of x and g of x both have a turning point at P. Okay, so where have we got P? Okay, so we essentially want to show that they have the same turning point, or verify that their turning point is the same. Okay, so we're going to need to show that both functions have a turning point at the same point. Okay, so we've now got a and b, so we've got our functions. So f of x is 12 minus x times x squared. Sorry, x times, what was it? X minus 2 squared. Sorry. Okay, so we're going to need to differentiate that. So we could use a product rule, but it's not difficult to expand it, so let's just do that. So we're going to have 12 minus x times x minus 2 all squared is a perfect square. It's x squared minus 4x plus 4. So we get 12 minus x cubed minus plus 4x squared minus 4x. Okay. So the derivative of that, derivative of 12 is 0, derivative of negative x cubed is minus 3x squared plus 8x minus 4, and that's going to need to equal 0 for the turning points. Factorising with a negative coefficient of x squared is complicated, so I'm going to multiply everything by negative 1. Factors of positive 12 that add up to negative 8, so that's going to be minus 2 and minus 6. So we split the middle term. Go back to some of my Year 10 videos on factorising if you need a refresher on this. Group. So we're going to have 3x times x minus 2 times x minus 2. And so it's x minus 2 is a common factor times 3x minus 2. Okay, so f dash x has turning points at x equals 2 and 2 and 2/3. And we solve those, equal to 0. Now it looks like g of x, we can see that f of x has 2 turning points, so that's going to be the one at 2/3 and that's going to be the one at 2. But let's also confirm that g of x has a turning point at 2. So g of x, the equation for g of x, and then we can find where that turning point is. So g of x, where's the equation here? 12x plus bx squared, and b was negative 3, so it's 12x minus 3x squared. So parabola is a bit different with finding a turning point. I mean, we could differentiate and solve equal to 0, but we could also, if you factorise this, you're going to have 4 minus x. So you've got intercepts at 0 and 4, and so therefore the turning point is going to be halfway between them. But you know, just make sure that you give adequate justification for that. You could also use negative b on 2a, or I could just as easily differentiate. It's not particularly complicated. Solve it equal to 0. So 6x equals 12, and so x equals 2. Okay. So therefore, what do we know here? Oh, sorry, struggling with the eraser today. Okay, let's go again. So therefore, both f and g have turning points, well, stationary points, but we can see from the graph that they're turning points at x equals 2. Okay, so this tells us that the x coordinate of P is 2. So let's go back and read the question. So verify that f and g both have a turning point at P. And so they both have a turning point at, so actually I'd probably just find the, so I was thinking we've identified they both have a turning point at 2, but that actually doesn't verify that it's the same point. So we can see on the graph it looks like it is, but we actually need to show that both of them go through the same coordinates. So I'm just going to skip my conclusion for now. I'm going to actually find the y coordinates of the turning points on both graphs so we can confirm that it's indeed exactly the same point. Okay, so let's go back and do f at 2 with this one. Let's go back to the original version of the function so we don't have to do a whole lot of, you know, cubing, etc. Okay, so actually if we sub 2 back into this original, sorry, lost my pen there, back into this original, we're going to get 2 times 2 minus 2 there is 0, so that whole second part is 0, and so we're just going to get 12. Okay, so that's nice. Okay, so there is a turning point at 212. And then for g of x, we're going to get g of 2, which means we get 12 times 2 minus 3 times 2 squared. So that's 24 minus 12. And so that is also 12. And so we have a turning point at 212. Okay, so therefore, let's draw a conclusion here. Therefore, both f and g have a turning point at 212, and therefore the coordinates of P are 212. Okay, so that was what we needed to do. Let's just go back and check the question before we move on. Sorry, my computer had a little spasm there. Verified that F and G both have a turning point at P, so we verified that they both have a turning point at 212, and so therefore the coordinates, that must be the point P, and so therefore the coordinates of point P are 212. Okay. Alright, let's go here. So part C. A theme park is planned whose boundaries will form the triangle OAB, where O is the origin, A is at K0. Okay, so this point here is K0. O is the origin, and obviously B is at KG of K. Let's just get what the rule for G of X is again here, so we can see it. It was 12x minus 3x squared. Okay, we also found that this was 212. Don't know whether that's useful, but let's just make sure we've got everything we know here. Okay, so we've got this triangle as shown below where k is between 0 and 4. Okay, and that's because the x-intercepts of g of x are, if we take out that factor of 3x, the x-intercepts of g of x are at 0 and 4, so this point here is 4, 0. So k has to be less than 4, so the triangle's within the picture that we can see here. Find the maximum possible area of the theme park in kilometres squared. Okay, so the theme park has the boundaries of this triangle. Okay, so the question is to find the maximum possible area of the triangle. All right, so therefore we need to come up with the area of the triangle. Okay, I'm going to define the area of the triangle as being A of K. So I'm going to come up with an equation for the area. So A of K is going to be, it's a triangle, so it's half times the base length is clearly K, and the height of the triangle is clearly G of K. So we're going to have half times K times G at K. So if we put K into our G of X function, we're going to have, what was it again? 12K minus 3K squared. Alright, so if we expand that out, we're going to have 6K squared minus 3 on 2K cubed. Alright, we want to maximise that area. So I'm going to look at solving the derivative of that equal to 0. So derivative of that gives me 12K minus 9 on 2K squared, and that has to equal 0. We're looking for the stationary points of the area function. So we can factorise this. If we take out K, we get 12 minus 9 on 2K. And so we get K equals 0, or that, which isn't very fun, but that's okay, equals 0. So that means 9 on 2K equals 12. Multiplying both sides by 2. 9K equals 24. And then dividing both sides by 9. It's a common factor of 3 there, so that's 8/3. Okay, so K equals 0 or K equals 8/3, but we already know that K can't be 0 because K has to be between 0 and 4. Okay, But we probably need to, and diagrammatically we can see that, again, we know that this is 2 here. 8/3 is going to be, sorry, why did I just write 2? Why did I just write 8? I mean, that's 2 there. 8/3 is a bit more than 2. It's 2 2/3, okay? So it's going to be, let's say, here. So what we're saying is that that gives maximum area. If k was 0, that's when we would get minimum area, okay? So that looks to give us maximum. It doesn't ask us to justify maximum, but I always like to be sure that I get a maximum area. Let's also be clear in the question. So find the maximum possible area of the theme park. Okay, so first of all, I'm going to confirm that k equals 8/3 gives me maximum area. So I'm going to work out the derivative at that value and therefore work out what that tells me about the shape of my area function. So it's not the shape of the graphs up there, it's the shape of the area function, because we want to make sure we've got the maximum area. So 8/3, as I said, is a bit more than 2. And so therefore values either side of that would be 2 and 3. So if we put 2 into our derivative function, we're going to get 2 times 12, which is 24, minus 9 on 2 times 4. So it's going to be 9 times 2. Sorry, let me just jot. So what did I just say? I'm doing 24 minus 9 on 2 times 4. 9 on 2 times 4 is just going to be 9 times 2. So it's 24 minus 18. And so it's going to be 6. This is clearly 0. And if I sub 3 into my derivative function, I'm going to get 36 minus 9 on 2 times 9, which is 36 minus 18 on 2. Sorry, not 18 on 2, 81 on 2. Which is 36 minus 40.5. So it's definitely negative. What's that going to be? Negative 4.5. So we have positive gradient, zero gradient, and negative gradient. Okay, and so we know that the maximum area occurs when k equals 8/3, which means that maximum area is a at 8/3. And let's go back to our area function. So we're going to have 6 times 8/3 squared minus 3 on 2 times 8/3 cubed. Okay, so that means we get 6 times 64 on 9 minus 3 on 2 times minus, now actually it might be easier to go into the factorized form of g of x. Sorry, factorized form of a of k, just because then we don't have to cube that 8/3, which I'm trying to avoid doing if I can. So if we have a think about this, if we even just take out a k, it's going to be 6 minus 3 on 2 times k squared. Sorry, take out k squared. I'm just wondering if that's actually going to give me an easier calculation so I don't have to work out 8 cubed, which we could, but again, let's see if we can be a bit strategic about our number work. So we're going to have, it is going to be 8/3 squared, and then it's going to be 6 minus 3 on 2 times 8/3. So that's already nicer because those 3's are going to cancel out, and that 8 on 2 is just 4. So this is a much nicer way to do it. 864 on 9 times, this is going to be, that's 1, that's 1, that's 1, and that's 4. 6 minus 4 is 2. And so we're going to get 128 on 9. and we had everything was in kilometres, and that's an area, so that is kilometres squared, and this K value was in kilometres. So the maximum area of the theme park, the maximum possible area we could create that yellow triangle if it's bounded underneath the dashed parabola g of x, is going to be 128 on 9 kilometres squared. And to be honest, as a last question on exam 1, that's also a fairly routine thing, maximising the area of a triangle or a rectangle underneath a curve. So I really do think it was a fairly routine exam conceptually, but it was the number work that was difficult. And so it's really important to be practicing that ability to work with fractions, decimals, simplify quite complicated expressions.